Hi, everyone. Thanks for tuning in for my talk. I'm going to talk about um, this recent work. Is it easier to prove theorems that are guaranteed to be true? This is joint work with Rafael. Arguably, P versus NP is the biggest open problem in computer science. But this might not be the most important question. Even if NP is hard in the worst case, it could be easily solvable in practice. Maybe the instances that occur in practice are easily solvable. One could think that NP problems could be efficiently solved with high probability for all efficiently sampleable distributions. And in real life, it could be that we encounter only efficiently sampleable distributions. Motivated by this, Gurvich in 89 and Impagliazzo back in 95 considered the following game between a challenger and a solver. In fact, Impagliazzo called this a game between Professor Gauss and Friedrich Gauss, where the challenger is going to sample from some language L according to some distribution D, and Gauss needs to tell whether this instance is in the language or not, and if it's in the language, produce a witness. Now, the hardness of this language, or the average case hardness of this language, is in fact captured by the success probability of Gauss in this game. One unsatisfactory part of this game is that while these instances can come from an efficiently sampleable distribution D, the solutions might not be efficiently verifiable. In fact, for a hard language, for a hard NP language, one cannot verify whether when Gauss says that it's not in the language. In fact, the question that we want to ask here is it easier if these sample statements were promised to be true? Because in this case, Gauss would have to produce a witness, and that is efficiently verifiable. In fact, this was, motivated in early works due to Ivan and Jacobi, and Ivan, Selman, and Jacobi, where they asked for hardness of instances that are promised to be true. They were motivated by cryptography. For example, in public key encryption, you want security to hold only for correctly generated or valid ciphertext. And in fact, this also motivated them to introduce promise problems. The open problem that we want to address in this work is, does the average case hardness of NP imply the average case hardness of problems that are promised to be true? In this work, we show that the answer to this question is in fact yes. So let me begin with just talking about what is what does it mean to say that NP languages are hard on the average? This was formalized by Knuth and Levin in the 70s and 80s, and here we are giving a slightly different version of their definitions. And there is a decision version and a search version. The decision version asks that no attacker be able to decide instances sampled by some probabilistic polynomial times sampler D with probability better than 2/3. The search variant, on the other hand, additionally restricts the distributions to require them to produce instances in the language, with significant probability, and that no attacker can find a witness with probability better than 1/3. Now, the last variant that we also are interested in this work is promise true search problems. So here you require that the sampler produce instances only in the language, or produce instances in the language with probability 1, and no attacker can find a witness with probability better than 1/3. So first, I would like to talk about two natural subclasses of this class of promise-true NP search problems. The first class restricts the NP problems to where every instance is guaranteed to have a witness. We in fact know this class. It's a well-known complexity class referred to as total function NP, or TFNP, which is introduced in the work by Megiddo and Papadimitriou. The second class restricts the distributions to samplers that can sample both the instance along with its witness. In fact, this formulation is equivalent to a fundamental concept in cryptography, one-way functions. So I want to talk a little bit about the hardness of these two natural subclasses before I get into the meat of our talk. First, the class of TFNP. This, as I just mentioned, includes all search problems where every instance has a witness. An alternative formulation is search problems in NP co-NP. Hardness in TFNP actually has been established from concrete cryptographic hardness assumptions, specifically collision resistant hash functions and one-way permutations. However, it's not known whether it's implied by the existence of one-way functions. TFNP, in fact, also captures some important class of problems. Um, for example, machine learning or local search. Here you're given three polynomial time algorithms, init, neighbor, and cost. And the goal is given a starting point given by the init algorithm, you want to find a point that has the smallest cost with respect to all of its neighbors. Now, just viewing this as a tag, you know that there always exists a solution. This is an example of a problem in TFNP. Another problem is computing the Nash equilibrium. In fact, a famous theorem by Nash in 1951 shows that every finite game has a Nash equilibrium. But can we efficiently find it? In fact, this problem is complete for a subclass of TFNP referred to as PPAD. And even this subclass, hardness has been established from cryptographic assumptions. So a related open problem here is, does average case hardness of NP imply average case hardness of TFNP? There's in fact evidence for and against. There are black box separations that show that such an implication can't hold. And in a couple of years back, Hubacek, Nauer, and Yogev actually showed that this implication is true under a strong de-randomization assumption. The second class of problems defined by one-way functions. In fact, one of the original motivations for studying average case hardness came from from the works of Diffie, Hellman, and Levin in the 70s and 80s. And here, the question is, it's not just that you want to sample hard instances in an NP language, but also you want to be able to sample instances together with their solutions. One-way functions, we know the existence based on various number theoretic and lattice conjectures. It's central to cryptography. It is equivalent to many of the cryptographic primitives that we use, and in fact implied by most cryptographic objects. A second related open problem in the intersection of complexity and cryptography is, does average case hardness of NP imply the existence of one-way functions? Here again, we have evidence for and against. There are black box separations that rule out such an implication, and such an implication can be established under some additional assumptions. Ostrowski and Wigderson showed that assuming zero knowledge for all of NP, you could establish the existence of one-way functions from average case hardness of NP. And more recently, by Komorogotsky et al., they showed assuming indistinguishability obfuscation. So in this talk, we're also going to talk about these related open questions. Does average case hardness of NP imply either the average case hardness of TFNP or the existence of one-way functions? And note here that solving either one of these open questions also solves the open problem that we are interested here, whether average case hardness in NP implies average case hardness of promise true NP search, as each of these are subclasses of this problem. And what we show in this talk is, in fact, answer is yes to at least one of these two questions. So we say either the first implication should hold or the second one. The key notion that we are going to use to prove this result is interactive puzzles. I'm going to start with a slightly different view of average case hardness of NP. It is syntactically the same as what I defined before. I'm going to view this as an interaction between a challenger and an attacker. The challenger samples some x according to a distribution D, and the attacker produces a W, followed by the challenger accepts this if x comma W holds with respect to some relation. Average case hardness requires a non-triviality condition, which says that for all n, the x that is sampled by the challenger must be in the language with probability 2/3. We call this the non-triviality condition. And the hardness requires that no attacker be able to produce a witness or make the challenger accept with probability at least 1/3 for all n. There are two variants to define here. One is called infinitely often, and the other is almost everywhere. The way I've defined here is infinitely often. Um, but the ones that come in cryptography typically are almost everywhere hardness. But for the purpose of this talk, I am not going to focus on this difference. Please look at the paper for how we deal with this. Average case hardness of TFNP replaces the non-triviality condition in this definition with a totality condition where we require that every instance that is sampled by this distribution that exists a witness. One-way functions naturally fit in this framework, where a challenger samples a random input R, applies the one-way function, and asks the attacker to invert the function with respect to f. And the hardness condition here is that there exists no attacker A that can make the challenger accept with probability 1/3. As stated, this is not a strong enough one-way function for being used in practice. But however, this does imply a weak notion of one-way functions that we know using standard techniques to amplify it to make it a strong one-way function. Again, here, the almost everywhere and infinitely many, you can formulate one-way functions in one way or the other, but I'm going to ignore this difference for this talk. Now, making this definition just an alternative definition more in line with NP search problems, we can think of this where the challenger samples instances along with the witness. And here, there is no non-triviality condition, but we require that the distribution can sample both an instance along with the witness such that the relation holds. And the hardness is the same as before. No attacker can make the challenger accept with probability 1/3 for all n. Um, So the main theorem here is that we prove here is if NP is hard on the average, then it implies promise true NP search is hard on the average. In fact, we show something that is stronger. We show that hardness must lie in one of these two subclasses, that either TFNP is hard on the average or that exists one-way functions. Answer to at least one of these, one of the related open problems must hold. Another view of this statement is that in Impagliazzo's worlds, specifically in Pesiland, where we know that NP is hard on the average, but one-way function do not exist, TFNP is hard on the average. I'm going to start with a quick overview of what you're going to see in the rest of the talk. Here's the outline. So we're going to introduce the notion of interactive puzzles that generalizes the notion of average case hardness. And then we're going to show that the existence of a two-round puzzle is equivalent to average case hardness of NP. Additionally, if a two-round puzzle is perfectly complete, it implies average case hardness of TFNP. Then we established the main lemma over here, which is a round collapse theorem for interactive puzzles. We show that if one-way functions don't exist, we can collapse a k-round puzzle to a k-1 round puzzle. In particular, if I have a constant round puzzle, we can get a two-round puzzle. And this collapse theorem holds while preserving perfect completeness. And finally, we'll be able to conclude our main theorem by by showing that one can turn two-round puzzles without perfect completeness to three-round puzzle with perfect completeness. And here we can use techniques from Führer et al. For interactive, who showed a similar result for interactive proofs. So what's an interactive puzzle? Well, it's an interaction between a challenger and attacker where the challenger in each round produces a random string and the attacker provides a response. And finally, the challenger accepts or rejects based on some polynomial time function applied on the transcript. There are two conditions for an interactive puzzle. First is non-triviality, which requires that there is an unbounded attacker that can make the challenger accept with probability 2/3. And the hardness condition says no probabilistic polynomial time attacker can make the challenger accept with probability 1/3. This is similar to Arthur Merlin games or public coin interactive proofs for the empty language, but with a computational soundness condition. In fact, the hardness over here can be thought of as the computational soundness for interactive arguments for the empty language. Now, 2/3 and 1/3 are, of course, arbitrary numbers. One can, amplify this using, standard parallel repetition theorems. And a perfectly complete interactive puzzle requires the non-triviality condition to hold with probability 1, meaning that an unbounded attacker can make the challenger accept always. So how does a two-round puzzle look? Well, the challenger gives a random string followed by the attacker response, and the challenger accepts if for some polynomial time predicate, returns 1 on the transcript. Now, the first observation is that, a two-round puzzle trivially implies average case hardness of NP. You can think of the first message as the instance and the response as the witness. Now, the next observation is that if NP is hard on the average with respect to the uniform distribution, then it implies a two-round puzzle. Now, a well-established result over here by Impagliazzo in 11 and 90 is that if NP is hard on the average, then NP is hard on the average with respect to the uniform distribution. So this establishes our first claim, which is that the existence of two-round puzzle is equivalent to average case hardness of NP. And furthermore, if the two-round puzzle has perfect completeness, then it implies that average case hardness of TFNP, as we can use the first message. As I said, the first message is the instance. If we have perfect completeness, then every instance has a witness. So the main question that we are going to show here is that does the existence of a k-round puzzle imply average case hardness of NP? And this is similar to round collapse theorems that have been established before. For example, the Babai-Moran's round collapse theorem proves this for information theoretically sound games. But these results, in fact, break when you think of computationally sound ones. So the two theorems that we are going to, that we show in our work is that a constant round puzzle implies a two-round puzzle. And this, as we just showed before, implies average case hardness of NP. And we also show, we study the complexity of interactive puzzles, and we show that existence of polynomially many round puzzles is equivalent to the assumption of P space not in PPP. So the main lemma that I want to talk about here is that if one-way functions don't exist, then k-round puzzles can be collapsed to k-1 round puzzles while preserving perfect completeness. And then how do we establish theorem 1 from this lemma? Well, if one-way functions do exist, then we know that this implies average case hardness of NP, and therefore it implies the existence of a two-round puzzle. And if one-way functions don't exist, we repeatedly apply our main lemma to the constant round puzzle. So I'm going to start with talking about the Babai-Moran transformation, and going to point out why it doesn't work for computationally sound protocols. So just for example, we're going to take a 3-round protocol um, where the attacker sends the first and last message. Now, the Babai-Moran transformation works as follows. In the transform protocol, the challenger is going to produce M independent challenges uh, as part of the second round. And the attacker needs to produce a single first message P1 and M second messages P21 through P2M. And this challenger is going to accept if each of the M induced transcripts for the original protocol is accepting for C. And these M induced transcripts are P1, R2, RI, and P2I. Now, what Babai-Moran showed was that this preserves soundness if you repeat it sufficiently many times, where M is at least sufficiently bigger than the length of the first message. And very quickly, how this works is that for every P1, based on the soundness of the original protocol, we know that a challenge R is good with probability at most 1/3. Now, if we repeat it sufficiently many times, it follows that for every P1, the fraction of challenges R1 through Rm are all good for P1 is at most 1/3 to the M. Now, by a union bound, the probability over all of these things that there exists a single P1 that will satisfy all of these things is going to be 2 to the P1 times 1/3 to the M. And this is negligible if you choose M sufficiently large. So this is how the case of information theoretic soundness works. But now, why does this fail for computational soundness? So let's take a simple example here. We have a simple protocol where the attacker first commits to a large database using a hash function. Then the challenger produces a random index and a bit B. And the attacker needs to open the database, and the challenger accepts if the ith entry of its database was B. Now, of course, this is computationally sound if the hash function is collision resistant. Now, if we apply the Babai-Moran transformation, now we can show that if I see all the challenges ahead of time, I can produce a database as long as these challenges don't have repeated indexes. There is an attacker that can always solve the collapsed protocol. So the main lemma we show is that while the proof idea and the technique, the proof idea from Babai-Moran transformation doesn't work, we show that if one-way functions don't exist, the transformation can still be shown to preserve soundness. And why does the counterexample that I just showed you before not hold anymore? Because I've assumed that one-way functions don't exist. If one-way functions don't exist, hash functions cannot be collision resistant. And I'm not going to go into the actual proof, but the couple of ideas that are used is if one-way functions don't exist, then we can sample almost uniform inverses for any polynomial time function, and then we show using proof techniques from previous parallel repetition theorems, and in particular using the Raz's sampling lemma. So to conclude the proof, the main lemma that we establish is a round collapse theorem for interactive puzzles, where we show that if one-way functions don't exist, a k-round puzzle can be collapsed to a k-1 round puzzle while preserving perfect completeness. And then we're going to show how to combine using the two observations that we've already made, which is that existence of a two-round puzzle is equivalent to average case hardness of NP, and a perfectly complete two-round puzzle implies average case hardness of TFNP. And this we combine with this observation that 2-round puzzles can be converted to 3-round puzzles with perfect completeness. So here is how it works. We start with the average case hardness of NP, we get a 2-round puzzle. Now, from this, we can apply the Führer et al. Transformation to construct a 3-round puzzle with perfect completeness. And then we apply a round collapse theorem to get a 2-round puzzle with perfect completeness, which we know implies average case hardness of NP. And recall again, the second round collapse theorem holds only if one-way functions don't exist. So either one-way functions exist or average case hardness of DFNP holds. So this is our main theorem. We show that one of these two implication holds, but more generally, we show that if NP is hard on the average, then promised true NP search is hard on the average. And we used ideas from literature, from interactive proofs and arguments, and we introduced the notion of interactive puzzles to tackle this question on average case hardness. We show in our paper that this round collapse theorem actually has various other consequences for interactive arguments. Thank you.